There are few moments in science when we sense, viscerally, that we may be on the verge of something extraordinary. Moments when the vast, silent canvas of the cosmos, for a brief instant, seems to speak. And now, just maybe, it has. In a small patch of sky, far from the glare of our own sun, orbiting a dim and ancient red star, there lies a world not like our own. It is heavier, larger, stranger. It is bathed in the ruddy glow of a star that will outlive us all. And yet, this planet, known only by the designation K2-18b, may be whispering to us across the interstellar dark. It may be whispering the signature of life, not a message, not a civilization, not yet, but something more primal. A molecule, a breath, a pattern in the spectrum of starlight that, if confirmed, could represent the first evidence that we are not alone in the universe. To some, it may sound unremarkable. After all, we've long believed that life must exist beyond Earth. The numbers alone are overwhelming, hundreds of billions of stars in our galaxy, each with the potential for planets. Life, we suspect, is not a miracle of Earth, but a probability of nature. But belief is not knowledge. Hope is not evidence. And so, we wait. We build our telescopes. We peer deeper into the cosmic dark, not to satisfy curiosity alone, but to find truth. And now, through the lens of the James Webb Space Telescope, we may have come closer than ever before. It began with water. In 2019, scientists using the aging yet still powerful Hubble Space Telescope observed water vapor in the atmosphere of K2-18b, a world more than twice the radius of Earth, orbiting in the habitable zone of its star, and now possibly hosting water. It was tantalizing, but not conclusive. Water alone is not life. Venus has water vapor in its clouds, and Mars once had rivers. Yet neither teems with the kind of vibrant biosphere we see here on Earth. Still, the signs were promising. Then, in 2023, Webb turned its gaze to the planet. With infrared vision far superior to any observatory before it, it analyzed the starlight that filtered through the planet's atmosphere during transit when K2-18b passed in front of its host star. And what it found sent ripples through the scientific community. Not just water, but methane, carbon dioxide, and perhaps, just perhaps, dimethyl sulfide. Here on Earth, dimethyl sulfide is produced almost exclusively by life. It is the molecule you smell near the sea, a byproduct of phytoplankton, the tiny organisms that form the base of the marine food chain. It is not a chemical easily formed by volcanic processes or photochemistry. If it truly exists on K2-18b, it may represent something profound, a biosignature. A sign that, in the vastness of space, biology has emerged a second time. Let us pause for a moment and consider what that would mean. For centuries, we have speculated about life elsewhere. It has inspired our fiction, our philosophy, even our fears. But never, until now, have we had something like this, tangible, measurable, scientific. If life has begun on K2-18b, then it has begun twice in the universe, once on Earth, and once 124 light-years away. And if it can begin twice, it may be everywhere. That realization alone would transform our understanding of biology. It would tell us that life is not an accident, but a feature of the universe. That the same laws of chemistry and physics that govern the stars and galaxies also give rise to molecules that replicate, evolve, and eventually wonder. But we are not there yet. Science demands caution. The detection of dimethyl sulfide is still tentative. A 3 sigma signal, meaning there's a 0.3% chance it's a statistical fluke. Significant, but not definitive. To claim the discovery of life, we will need more data, more observations, perhaps years of study. And yet, we are close, so close. In this documentary, we will explore the full story of K2-18b, how it was discovered, what we know of its nature, and what makes it such a compelling candidate for extraterrestrial life. We'll dive into the chemistry, the physics, and the astrobiology of this world, and we'll ask a question that has haunted science for decades. This planet, K2-18b, may not give us that answer, but it might offer the first clue. And from there, everything changes. Because if we can detect one, we can detect many. If biology is out there, it will not remain hidden for long. We are no longer just observers of the stars. We are listeners, interpreters, seekers of meaning in molecules. And the next great revelation may not come from within our own minds, but from the light of an alien world. K2-18b, an ocean world hidden in starlight. It is a strange truth of our time that we are now more familiar with the atmospheres of planets light years away than with the depths of our own oceans. But perhaps it is not so strange. The universe beckons in ways that the Earth does not. It reveals its secrets to those with patience and light, and above all, to those who know how to listen. K2-18b is one of those secrets. It is a planet that orbits a star known simply as K2-18, a small red dwarf located 124 light-years from Earth in the constellation Leo. It does not shine brightly in our skies. You could not see it with the naked eye, and yet it has become the focus of intense scrutiny, not because of what it is, but because of what it might hold. Let us consider the fundamentals. K2-18b is what astronomers classify as a sub-Neptune. It is roughly 2.6 times the radius of Earth, and 8.6 times as massive. If we could stand upon it, and we probably couldn't, its surface gravity would be nearly twice that of Earth. A human body would feel heavy, burdened, as though the planet itself were trying to keep you close. But we likely would not stand on it at all, because K2-18b is almost certainly not a rocky planet. It is enveloped in a thick atmosphere, rich in hydrogen and helium. And beneath that atmosphere, if the models are correct, lies a vast global ocean. This class of exoplanet is still theoretical. We call them Hycean worlds, planets with deep oceans of liquid water beneath hydrogen-rich skies. They are unlike anything in our solar system. Not gas giants like Neptune, not rocky worlds like Earth, but something in between, a hybrid of atmosphere and ocean. Heat and chemistry, wrapped around a planetary core we cannot see. For decades, scientists imagined that life elsewhere would require a planet like ours, solid surface, moderate temperatures, thin atmosphere. But our observations have forced us to reconsider. Hycean worlds may be far more common than Earth-like ones, and they may, in many ways, be better suited for life, particularly microbial life that thrives in aquatic environments. On Earth, the first life emerged in water, perhaps in shallow pools heated by volcanic springs, or perhaps in the cold darkness of the ocean floor, near hydrothermal vents. These environments were protected, chemically rich, and persistent. Could the same be true for worlds like K2-18b? Let us examine its star. K2-18 is a red dwarf, the most common type of star in the galaxy, smaller and cooler than our Sun. Red dwarfs burn their hydrogen slowly, with lifespans measured not in billions, but in trillions of years. They are cosmic elders, destined to outlast even the last white dwarfs in the distant future. K2-18b orbits its star every 33 Earth days, placing it squarely within the habitable zone, the region where temperatures may allow for liquid water to exist on a planet's surface, or beneath its clouds. But red dwarfs are a mixed blessing. Because their habitable zones are so close to the star, planets within them often become tidally locked, with one side perpetually facing the star and the other cast in eternal night. They are also vulnerable to stellar flares, bursts of radiation that can strip away atmospheres and sterilize planetary surfaces. Yet there is hope. Recent studies suggest that some red dwarfs, like K2-18, may flare less frequently, and a thick hydrogen atmosphere could protect the oceans below from radiation. If such a world is indeed covered in water, then even a tidally locked configuration might still allow life. Circulation of heat through atmospheric winds or ocean currents could keep the planet temperate and stable. It is difficult to imagine what such a place would look like. If you could descend through the atmosphere of K2-18b, the light would grow dim and red. The sky would not be blue, but a murky, copper hue. Clouds would gather thickly, laden with vapor, refracting starlight into strange patterns. And below, Perhaps an ocean, an endless sea without continents or islands, no shore to stand on, no mountains to climb, just liquid depths and chemical complexity. In that alien sea, shielded from the harshness of space by kilometers of atmosphere and hydrogen gas, life might begin, not as complex animals or thinking minds, but as single-celled organisms, microbes, plankton-like entities that drift, metabolize, reproduce. In other words, the kind of life that gave birth to all others. Of course, we cannot see that ocean directly, not yet. What we have, instead, is spectroscopy, a science of inference. When K2-18b transits its star, a small fraction of starlight passes through its atmosphere before reaching our telescopes. Certain molecules absorb certain wavelengths of light, creating a fingerprint, a set of absorption lines that tell us what gases are present. That is how we know about the water vapor, the methane, the carbon dioxide, and perhaps, most intriguingly, the dimethyl sulfide. None of these molecules alone prove that life exists on K2-18b. They can all be produced by non-biological processes, volcanism, photochemistry, reactions between rock and gas. But together, in the specific ratios observed, they are suggestive. On Earth, this combination is found almost exclusively in marine biospheres, in ecosystems driven by microbial life. It is not a discovery, but it is a possibility, one that grows stronger with every observation and every new piece of data. K2-18b has become, in many ways, our first real candidate for an inhabited world, not a mirror of Earth, but something more ancient, more elemental, a planet of oceans and molecules, chemistry and time, and perhaps, if we are fortunate, a planet where life has taken root in the darkness beneath the clouds. What would that mean? It would mean that life is not the rare consequence of planetary coincidence, but the natural product of planetary chemistry. It would mean that the universe does not just allow for life, it encourages it. And it would mean that we are not alone, not even close. What the molecules are telling us. No song sung beneath the stars, no whispered declarations drifting between the galaxies. And yet, the universe speaks. It speaks through light, through the long, patient journey of photons across millions of years. It speaks in patterns, in the gentle sway of gravity, the symmetry of atoms, the geometry of orbits, and sometimes it speaks in the language of molecules. On a world like K2-18b, we cannot yet see oceans or clouds or distant shores. We cannot send spacecraft to skim its atmosphere or dive beneath its waves. But we can catch a few rays of starlight, filtered through its sky, stretched and shifted by its chemistry. From this light, we read its story. When the James Webb Space Telescope observed K2-18b in 2023, it did so not by imaging its surface, but by observing a transit when the planet passed in front of its host star, blocking a tiny fraction of its light. As this light passed through the planet's atmosphere, certain wavelengths were absorbed by gases, while others were allowed to pass. The result was a spectral fingerprint, a barcode of sorts, etched in infrared. It was this fingerprint that first confirmed what Hubble had already suggested: water vapor in the atmosphere of K2-18b. Not ice, not liquid, but vapor suspended in its upper atmosphere, possibly condensing into clouds. This was important. But it was only the beginning. Alongside the water, JWST detected methane and carbon dioxide, both carbon-bearing molecules, both vital in the story of life on Earth. And then came a surprise. The data contained hints, faint but persistent, of dimethyl sulfide, or DMS. Let us begin with the more familiar molecules, methane and carbon dioxide. Methane, on Earth, is produced in two main ways. It can arise abiotically through geological processes like serpentinization, where water interacts with certain types of rock under high pressure and heat. It can also come from biological activity, from microbes in wetlands, from the digestion of animals, from the decomposition of organic matter. Carbon dioxide is similar. It is a byproduct of combustion, of respiration. of volcanic activity. It is both a lifeline and a danger, essential for warming Earth but catastrophic in excess. The presence of both CH4 and CO2 on K2-18b in itself does not confirm life, but the ratio of these gases is curious. On Earth, their relative abundances are tightly linked to biological cycles. Methane is quickly destroyed in our atmosphere by sunlight and chemical reactions. If it is present in significant quantities, it must be constantly replenished. The same appears to be true on K2-18b, which raises the question, what is maintaining the balance? Is it chemistry? Is it geology? Or is it biology? Now we come to dimethyl sulfide, the molecule that has caused such a stir in the astrobiology community. On Earth, DMS is not just produced by life. It is, as far as we know, produced only by life. More specifically, it is released by marine phytoplankton, microscopic organisms that inhabit the sunlit layers of our oceans. As they die and break down, they release dimethylsulfonylpropionate, which is then converted into DMS. It rises into the air, influencing cloud formation and even the planet's climate. It gives the sea its smell. And if the detection on K2-18b is real, and that is a significant if, it would suggest not just chemistry, but biology, a biosphere, a living ocean. But how confident can we be? The detection of DMS was made using JWST's mid-infrared instrument, MIRI. It was independent from the earlier measurements made by its NIRS-SPEC and NIRIS instruments. That's important. It means the signal didn't come from noise in a single channel, or an artifact of a specific instrument. Statistically, the detection sits at 3 sigma. That means there is a 99.7% chance the signal is real, and a 0.3% chance it is a fluke. In physics and astronomy, we typically require a 5 sigma detection, corresponding to a 1 in 3.5 million chance of being wrong, before claiming a discovery. The team behind the DMS claim has requested more time with JWST to confirm their result. If granted, and if the signal holds, it will likely become the strongest biosignature candidate in the history of observational astronomy. Still, caution is warranted. There are non-biological pathways for methane and carbon dioxide. DMS is harder to explain, but not impossible. It could be a byproduct of some exotic photochemistry in hydrogen-rich atmospheres. Perhaps a process we have not yet seen on Earth, or not under the conditions of K2-18b. Astrobiology, by its nature, walks a fine line between evidence and enthusiasm. We want to believe, but belief must wait for confirmation, and so the debate begins. Could this be a new class of chemical system? A prebiotic chemistry producing DMS analogs? Could it be a fluke? A data reduction artifact? A misidentification? To strengthen the case, researchers turn to models. They simulate K2-18b's atmosphere under different assumptions: volcanic outgassing, photochemical equilibrium, hydrothermal vents, and again, the models suggest that abiotic sources struggle to produce the observed concentrations of these gases together, especially DMS. Moreover, the concentrations are high, significantly higher than what we see on Earth. That's surprising, but not necessarily problematic. In fact, some theoretical work had predicted exactly this outcome for Hycean worlds with life. A thick hydrogen atmosphere traps heat and slows chemical reactions. Gases that would quickly dissipate on Earth could linger far longer. And in an ocean world without continents or seasonal turnover, microbial life could dominate the biosphere almost entirely, leading to a planet-scale bloom of organic chemistry. In short, the fingerprint matches. It is not proof, but it is not coincidence either. There is, of course, one more tantalizing possibility. If K2-18b is not an ocean world, but a small gas dwarf with no surface, then the presence of DMS becomes far more difficult to explain by natural processes. There would be no ocean in which microbes could thrive, no seafloor, no hydrothermal vents, just gas. In that case, the detection would no longer be a biosignature. It would be something else entirely. It would be a technosignature, a sign not of biology, but of technology, of intelligent life releasing complex molecules into its atmosphere. There is no reason to believe that is the case, but it cannot be dismissed out of hand. Because once you eliminate the biological and the geological, what remains? And so, we are left here, suspended between hope and hypothesis, between signal and noise. The molecules are whispering. They may be speaking of biology, or chemistry, or something we have never seen before. If K2-18b holds life, it will reveal itself not with trumpets and declarations, but with molecules drifting silently in the light of a red star. All we need to do is continue to watch. Could life thrive there? To ask whether life exists on K2-18b is to ask more than whether molecules can survive there. We are not merely seeking chemistry, we are seeking biology. Not atoms, but cells, not reactions, but replication, and that is a far deeper question. Because life, once begun, is persistent. It adapts, it evolves, but to begin, to truly take hold, it needs more than the right molecules. It needs an environment that can sustain it, protect it, nourish it, let it grow. Could K2-18b be such a place? Let us imagine, not from the stars above, but from the sea below. Beneath its thick hydrogen-rich atmosphere, K2-18b may conceal a vast global ocean, perhaps hundreds of kilometers deep. Unlike Earth's oceans, it would have no continents, no islands, no shallows, no shores on which to crawl and evolve limbs, just water, deep, dark, and endless. At the top, the ocean would be blanketed by an atmosphere rich in vapor, perhaps turbulent with clouds. But as you descend, the light would vanish, filtered by kilometers of water. The pressure would rise to unimaginable levels, and somewhere far below, there might be a rocky core, a silent surface warmed by the slow release of radioactive heat and tidal forces. It is here, in this profound darkness, that life might begin. On Earth, life may have originated in just such a place. Hydrothermal vents, deep beneath our oceans, are cracks in the seafloor where heat and minerals pour into the surrounding water. Around them, entire ecosystems thrive, ecosystems that do not rely on sunlight, but on chemistry, on chemosynthesis, on the conversion of chemical energy into biological order. Tube worms, giant clams, and swarms of microbes form colonies around these vents, bathed not in light, but in sulfur. If K2-18b has such vents, they could be cradles of alien life. Even in the absence of a rocky surface, there may be floating layers of water ice or supercritical fluids that allow for chemical gradients, gradients that drive metabolism, that allow molecules to store and release energy, the fundamental requirement of life. The ingredients may be there. The processes may be there. The question is, can life, once sparked, thrive? Let us consider the challenges. The most obvious is gravity. K2-18b is significantly more massive than Earth, which means its surface gravity could be nearly twice as strong. On land, that would make life difficult. Walking, flying, even circulation of fluids within organisms would be more taxing. But in water, gravity's effects are softened. Buoyancy helps. Organisms float, drift, swim. The ocean becomes a protective womb. Indeed, the earliest life on Earth remained in water for billions of years. Complex, multicellular organisms evolved under the surface long before the first fish ever contemplated the land. So perhaps gravity would not be an obstacle, at least for microbes and other soft-bodied creatures. On Earth, sunlight powers the biosphere. Photosynthesis turns light into sugar. But if K2-18b is a Hycean world, its oceans may be so deep and its clouds so thick that sunlight never penetrates far. Photosynthesis, at least as we know it, may be impossible. But again, Earth shows us a way forward. In the deep sea, life thrives without sunlight. Chemosynthetic organisms use hydrogen sulfide, methane, and other compounds as energy sources. Similar processes could exist on K2-18b, where abundant hydrogen and carbon-based molecules offer potential fuel for alien metabolism. Perhaps, in the darkness beneath its clouds, Entire ecosystems have evolved based not on light, but on chemistry. Still, one must ask, could life evolve intelligence in such a place? This is a more delicate matter. Intelligence, at least in the form we understand it, arises from complexity, from ecological interactions, long-term memory, communication, and environmental pressure. Life in a featureless, endless ocean may lack many of these drivers. Without land, there are no tools, no fire, no metallurgy. Even building a shelter becomes difficult. How does one smelt metal in a deep ocean? How does one harness electricity? In short, even if life thrives, it may remain simple, and that may be the answer to one of the deepest mysteries in all of science, the Fermi paradox. The paradox asks, if the universe is teeming with habitable planets, perhaps even with life, then where is everyone? Why do we not see evidence of advanced civilizations? No spacecraft, no signals, no ruins on the moon, no great Dyson spheres harvesting starlight, just silence. Perhaps the answer is this, but intelligence is rare. And not because evolution doesn't favor it, but because most life is born in worlds like K2-18b. Worlds with oceans but no land, with pressure but no fire, with chemistry but no tools. Civilizations may never arrive, not because they fail, but because they never had the chance. The universe may be filled with biospheres, but almost devoid of technospheres, a sobering thought, but also a hopeful one. It means we might find it elsewhere, on Europa, on Enceladus, beneath the ice of exomoons and dwarf planets. It means that we are no longer wondering if we are alone, but how many neighbors we have yet to meet. And perhaps, one day, we will not only observe them, but help them. Imagine a distant future in which humanity becomes the uplifter, the bridge between worlds locked in their oceans and the cosmos that waits beyond. We, born of a planet with both ocean and land, might be the rare creatures who escape, who travel, who share, who listen not just for voices, but for life itself, in whatever form it may take. We stand at a precipice, a species born of stardust, cradled on a singular pale blue sphere, yet possessed by an insatiable yearning to touch the very stars from which we came. It is a dream woven into the fabric of our consciousness, a whisper from the cosmos that beckons us outward, beyond the familiar comforts of our terrestrial home. But this dream, so luminous and compelling, collides with a reality far starker, far more unforgiving than our mythologies often portray. The universe, in its silent, sprawling majesty, is not a garden awaiting our arrival, nor a canvas eager for our imprint. It is an arena of profound contradictions, a realm where the very laws that govern its existence seem engineered for the extinction of fragile, water-based life such as ours. This is the story of that contradiction, of our audacious ambition to transcend our earthly origins, and of the immense, perhaps impossible, challenges that lie in wait. It is a journey into the heart of what it means to be human when faced with the ultimate frontier, a frontier that questions not only our capabilities, but the very essence of our being. We look up at the night sky, a tapestry of distant suns, and feel a pull, an ancient echo of our cosmic lineage. But what awaits us in that vast, indifferent expanse? Is it destiny, or is it a beautiful, perilous illusion? The quest to live beyond Earth forces us to confront these questions, to stare into the abyss and ponder our place within an existence far grander and more terrifying than we can easily comprehend. The story begins not with triumph, but with a fundamental truth: space is trying to kill you. The cosmic hostility and our earthly cradle. Space, in its stark and unyielding reality, is not the welcoming frontier of our most cherished fictions, but an environment intrinsically, almost deliberately, designed for our demise. This is not a turn of phrase meant for dramatic impact. It is a cold, hard assessment of the physical laws that govern the vast emptiness beyond our world. Consider the very notion of emptiness itself. The vacuum of space is so profound that it challenges our most basic sensory experiences. Here, sound, the medium of our voices, our music, the rustling of leaves, the crash of waves, simply cannot travel. The universe, from its very inception, established silence as its natural, dominant state, the cacophony of life, the symphony of a living planet. These are cosmic anomalies, fleeting whispers in an eternity of quietude. To step outside Earth's thin, precious atmospheric bubble is to enter a realm where your own heartbeat, the rush of air in your lungs, the words you might cry out, would be swallowed by an absolute stillness, a silence so complete it borders on the terrifying. This initial confrontation with the nature of space is but a prelude to the myriad ways the cosmos is engineered against us. Our planet, Earth, is a masterpiece of precise calibration, a sanctuary meticulously sculpted over 4.5 billion years to nurture the emergence and evolution of complex life. Every facet of our existence, every fiber of our being, is attuned to its specific conditions. Think of gravity, that constant, gentle pull that has shaped our skeletons, dictated the strength of our muscles, and engineered the intricate pathways of our circulatory systems, ensuring blood reaches our brains against its relentless tug. Our bones have developed a specific density to support our weight in this particular gravitational field. Our muscles have achieved a balance, strong enough for movement, but not so overdeveloped as to be inefficient. Then there is our atmosphere, not just a breathable mix of gases, but a crucial pressure vessel. This atmospheric pressure, something we rarely consciously perceive, is vital. It prevents the fluids in our bodies, our very blood, from boiling away at normal body temperatures. It acts as a shield, a multi-layered defense against the harshness of space. It burns up most of the meteoroids that would otherwise pummel our surface, and it filters out some of the sun's more harmful radiation. The exact composition of this air, roughly 78% nitrogen, 21% oxygen, and trace amounts of other gases, is no accident. It is the product of eons of biological activity, a life support system created by life itself. Beyond the atmosphere lies Earth's magnetic field, an invisible guardian generated by the churning of molten iron in our planet's core. This magnetosphere deflects the solar wind, a constant stream of charged particles flowing from the sun, and shields us from a significant portion of cosmic radiation. Those high-energy particles originating from distant supernovae and other violent cosmic events. Without this magnetic shield, the solar wind would gradually strip away our atmosphere, as it likely did to Mars, leaving the surface exposed and sterile. And consider our distance from the sun, the Goldilocks zone. Not too hot, not too cold, but just right for liquid water to exist on the surface. Liquid water, the solvent of life as we know it, the medium in which the complex chemistry of biology unfolds. This precise orbital placement is a cornerstone of our habitability. Our entire biological architecture, from the macroscopic design of our organ systems down to the microscopic machinery within our cells, is calibrated to function optimally within this one specific, extraordinarily rare environment. We are, in every conceivable way, creatures of Earth. So, what happens when this perfectly tuned organism is removed from its bespoke habitat and thrust into the alien conditions of space? The answer is swift and brutal. The body begins to betray its terrestrial heritage. In the microgravity environment of orbit, or the complete absence of gravity in deep space, the signals that have guided our physiological development for millions of years are suddenly absent or distorted. Bones, no longer needing to support weight against Earth's pull, begin to leach calcium. This demineralization occurs at an alarming rate. Roughly 1 to 2% of bone mass lost per month, a rate comparable to advanced osteoporosis in the elderly on Earth over extended periods. This leads to a significant weakening of the skeletal structure, increasing the risk of fractures upon return to a gravity environment or even during activities in space. Muscles must, too, begin to atrophy. Without the constant resistance of gravity, they lose mass and strength. This includes the heart, a muscle that has evolved to pump blood upwards to the brain against Earth's pull. In space, this task becomes easier, and like any underused muscle, the heart can begin to weaken and even change shape, potentially leading to cardiovascular problems. Fluids within the body, no longer pulled downwards by gravity, redistribute upwards, leading to a puffy face, sinus congestion, and a sensation often described as having a constant head cold. More troublingly, this fluid shift can increase intracranial pressure and put pressure on the optic nerve, leading to changes in vision, a condition known as spaceflight-associated neuroocular syndrome, or SANS, which has affected a significant number of astronauts on long-duration missions. The spine elongates as the vertebrae decompress without the constant compressive force of gravity, sometimes causing back pain and nerve issues. The delicate balance of the inner ear, which relies on gravity to orient us, becomes confused, leading to space adaptation syndrome, a form of motion sickness characterized by nausea and disorientation, affecting many astronauts during their initial days in orbit. And then there is the silent, invisible threat of cosmic radiation. Unfiltered by Earth's atmosphere and magnetic field, high-energy particles, protons, helium nuclei, and heavier ions called HZE particles stream through space, capable of penetrating spacecraft and human tissue. These particles can damage DNA within our cells, increasing the long-term risk of cancer. They can also affect the central nervous system, potentially leading to cognitive decline, memory impairment, and an increased risk of neurodegenerative diseases later in life. Our very cells seem to recognize the alien nature of space, initiating stress responses and altering gene expression in ways that suggest a fundamental incompatibility. The irony is profound. The universe that birthed the elements within us, that set the stage for our solar system's formation and the eventual emergence of life on Earth, is simultaneously an environment profoundly hostile to our continued existence beyond our planetary womb. Every system in our body, finely tuned over countless generations to the rhythms and pressures of Earth, finds itself adrift, struggling to cope with conditions for which it has no evolutionary precedent. This immediate biological rebellion is not merely an inconvenience to be overcome with clever engineering. It is a fundamental statement from our own physiology. It whispers and sometimes screams, a disquieting question if our bodies so violently reject the cosmos. Were we ever truly meant to live there at all? Earth, our cradle, meticulously prepared itself over geological eons, through volcanic upheavals, asteroid bombardments, atmospheric transformations, and the slow, patient dance of plate tectonics. It was a process of almost unimaginable duration and complexity, culminating in a world uniquely suited to us. Space, by stark contrast, offers only an immediate and lethal contradiction to our evolved nature, a constant reminder that we are at our core children of Earth, intricately and perhaps irrevocably bound to our home. The impossible dream of new Earths. The dream of establishing humanity among the stars, of transforming alien landscapes like Mars into verdant, habitable new Earths is a potent and enduring vision. It speaks to our exploratory spirit, our resilience, our innate desire to expand our horizons. Yet, this vision of rapid colonization, of achieving in mere decades or centuries what nature took billions of years to accomplish on Earth, collides forcefully with the harsh realities of planetary science and cosmic physics. Our own planet's journey to habitability was a saga of immense timescale and improbable fortune. 4.5 billion years of relentless geological and atmospheric transformation, of volcanic eruptions spewing gases that would form early atmospheres, of cataclysmic asteroid impacts delivering water and organic compounds, of the slow, grinding dance of plate tectonics recycling crust and regulating climate, and crucially, of the emergence of life itself, which gradually, painstakingly, transformed a poisonous early atmosphere into the oxygen-rich air we breathe today. This was not intelligent design in the conventional sense, but a breathtakingly complex interplay of chance and necessity, an incomprehensible stroke of luck played out over deep geological time. To imagine we can replicate this miracle on a world like Mars within the span of a few human generations is to underestimate the profound challenges involved. Mars, the red planet, is not a blank canvas patiently awaiting human artistry. It is a world that actively resists habitation. Its current state is a cautionary tale of planetary evolution. Once, perhaps, a warmer, wetter world with a thicker atmosphere and a protective magnetic field, Mars lost these life-sustaining attributes. Its smaller size allowed its internal heat to dissipate more quickly than Earth's, causing its core to cool and solidify. This led to the demise of its global magnetic field, leaving its atmosphere vulnerable to being stripped away by the relentless solar wind over billions of years. What remains is a thin, tenuous shroud, less than 1% the pressure of Earth's atmosphere, offering little protection from solar and cosmic radiation and incapable of trapping enough heat to keep the surface from freezing. The Martian surface is a desolate, cold desert. Its average temperature hovers around a frigid -80 degrees Fahrenheit, though it can plummet to -225 degrees in winter at the poles. Its atmosphere is predominantly carbon dioxide, unbreathable to humans. Its water, while present, is largely locked up as ice in the polar caps and underground permafrost, or has escaped into space. The soil, or regolith, is permeated with toxic perchlorates, chemicals that would need to be removed or neutralized before any large-scale agriculture could be attempted. And then there are the dust storms, colossal events that can engulf the entire planet for months, choking solar panels, abrading equipment, and posing a severe hazard to any surface operations. Every single day on Mars, for every human inhabitant, would necessitate a continuous, complex, and failure-intolerant technological intervention just to maintain the basic necessities of life: breathable air, liquid water, adequate warmth, and protection from radiation. If one could somehow stand on the Martian surface without a spacesuit, the experience would be horrifyingly brief. The low atmospheric pressure would cause the fluids in your body, the moisture on your tongue, in your eyes, in your lungs, and even your blood itself, to begin to boil at body temperatures in about 90 seconds. Your final conscious moments would be an excruciating agony as your body literally vaporized from the inside out. The universe's verdict on unprotected human life on Mars would be swift, unequivocal, and brutal. You do not belong here. Beyond the specific challenges of Mars, the very act of journeying into space is a testament to cosmic tyranny, a battle against fundamental physics. To escape Earth's substantial gravity requires accelerating a spacecraft to a velocity of approximately 11.2 kilometers per second, or about 25,000 miles per hour. The energy required to achieve this is immense. Consider the Saturn V rocket, the marvel of engineering that carried humans to the moon. It stood 363 feet tall and weighed 6.2 million pounds at liftoff. The vast majority of this mass was fuel, expended with ferocious intensity in mere minutes, all to deliver a tiny lunar module weighing just 32,399 pounds to the Moon, along with the command and service module. The inefficiency is staggering, akin to building an entire ocean liner to transport a single small suitcase across the Atlantic. And this monumental effort was merely to reach our closest celestial neighbor. The distances beyond the Moon become nearly incomprehensible, stretching the limits of our intuition. Mars, at its closest orbital approach to Earth, still lies an average of about 34 million miles away, though this can extend to over 250 million miles depending on orbital positions. Even with our most advanced current propulsion technologies, a one-way journey to Mars takes 6 to 9 months. During this transit, astronauts are confined to relatively small spacecraft, exposed to cosmic radiation and living in microgravity with all its attendant physiological challenges. Now consider the stars, the nearest star system to our Sun. Alpha Centauri is approximately 4.37 light-years distant. A light-year, the distance light travels in 1 year, is about 5.88 trillion miles. So, Alpha Centauri is over 25 trillion miles away. Our fastest outbound spacecraft, such as the Voyager probes, are traveling at speeds that, while impressive by terrestrial standards, are utterly dwarfed by interstellar distances. It would take Voyager 1 approximately 73,000 years to reach the vicinity of Alpha Centauri, assuming it were even heading in that direction, which it is not. 73,000 years, multiple generations, thousands of them, would live and die in transit, never knowing Earth, their planet of origin, nor their final destination, existing solely as links in a vast, unimaginably long chain of cosmic migration. The psychological and societal implications of such multi-generational voyages are profound and largely unexplored. This tyranny of distance and energy is mathematically enshrined in the Tsiolkovsky rocket equation, a fundamental principle of astronautics. It dictates that the change in velocity a rocket can achieve is directly proportional to its exhaust velocity and the natural logarithm of the ratio of its initial mass to its final mass. In simpler terms, to go faster or to carry more payload, you need exponentially more fuel. But more fuel means more mass, which in turn requires even more fuel to accelerate at that additional mass. This creates a vicious cycle, a mathematical reality that severely constrains our cosmic ambitions with current chemical rocket technology. It means that building spacecraft capable of rapid interstellar travel, or even rapid interplanetary travel with substantial payloads, faces enormous, perhaps insurmountable, hurdles with conventional propulsion. Thus, the dream of creating new Earths, of seeding humanity across the cosmos, is not merely an engineering challenge waiting to be solved with sufficient ingenuity and willpower. It is a confrontation with the fundamental scale of the universe, with the immutable laws of physics, and with the billions of years of unique evolutionary history that have made our own world habitable. The universe does not readily yield to our desires. It presents a series of obstacles so profound that they force us to question the very feasibility of our grandest cosmic aspirations, pushing the boundaries of what is possible and what may forever remain in the realm of dreams. The red dust of Mars and the distant, cold light of the stars serve as constant reminders of this immense, almost impossible challenge. The human element body, mind, and spirit in the void. Our very consciousness, that ephemeral yet profound phenomenon that allows us to gaze at the stars and contemplate our place among them, to formulate these grand dreams of cosmic expansion, is itself a product of exquisite biological fragility. It exists because of the precise and delicate arrangement of approximately 86 billion neurons in our brains, interconnected by trillions of synapses, all operating within a tightly controlled biochemical environment. This remarkable organ, comprising only about 2% of our body weight, consumes a disproportionate 20% of our body's oxygen and glucose, maintained at an exact temperature and pH balance. Disrupt this delicate equilibrium for mere minutes through lack of oxygen, a significant change in temperature, or a chemical imbalance, and the intricate dance of neural activity falters, higher cognitive functions cease, and the light of consciousness, as we experience it, dims and then extinguishes. This same hypersensitive consciousness, so dependent on terrestrial stability, is what we propose to send into environments that actively seek to undermine its very foundations. The long-term physiological decay experienced in space is relentless, a slow-motion dismantling of our Earth-evolved bodies, beyond the immediate challenges of bone demineralization, muscle atrophy, fluid shifts, and radiation exposure. There are more subtle, cumulative effects that we are only beginning to understand. The immune system appears to be dysregulated in space, with some functions suppressed and others overactive, potentially increasing vulnerability to infections or autoimmune responses. The microbiome, the complex ecosystem of trillions of bacteria, viruses, and fungi that live in and on our bodies and play crucial roles in digestion, immunity, and even mental health, is likely altered by the confined, sterile environments of spacecraft, the specialized diet, and the physiological stresses of spaceflight. The long-term consequences of these microbial shifts are largely unknown. Cognitive function itself may be impacted by long-duration space travel. While the heroic image of the sharp-focused astronaut persists, studies have hinted at potential subtle declines in certain cognitive domains, possibly due to a combination of factors including radiation effects on the brain, chronic stress, sleep disruption, altered cerebral blood flow, and the monotonous, confined environment. The very structure of the brain can change, with evidence of fluid shifts within the skull and alterations in white and gray matter observed in astronauts after extended missions. However, the assault on the human element is not solely physical. The psychological toll of long-duration space missions, particularly for future colonists who may face lifetimes of isolation and confinement, is a profound concern. Humans are social creatures, evolved in open spaces, under blue skies, surrounded by the rich sensory tapestry of a living, breathing planet, the scent of rain, the feel of wind, the sounds of nature, the vibrant colors of a forest or a sunset. What happens to the human psyche when confined for years or even generations within the sterile, metallic corridors of a spacecraft or a Martian habitat, where every square foot is meticulously engineered and maintained at tremendous cost, where there are no natural horizons, no unpredictable weather, no spontaneous displays of natural beauty beyond the porthole view of a distant Earth or an alien landscape? Studies of individuals in isolated and confined environments on Earth, Antarctic research stations, submarine crews, long-term prisoners, reveal a spectrum of psychological challenges: depression, anxiety, irritability, interpersonal conflicts, sleep disturbances, and cognitive decline, often referred to as the third quarter phenomenon, where morale dips significantly partway through a long mission. These terrestrial analogs, however, occur under Earth's familiar gravity, with the knowledge that the natural world, friends, and family are ultimately reachable. For space colonists on Mars, millions of miles from Earth, the isolation would be far more profound, the confinement more absolute, and the possibility of return, if it exists at all, would be a distant and complex undertaking. The psychological weight of knowing that your survival and that of your community depends entirely on the flawless functioning of complex human-made technology, with no natural safety net, would be immense and unrelenting. Yet, amidst these challenges, there is also the potential for profound, even transformative, human experiences. Many astronauts who have viewed Earth from orbit or the Moon have reported a cognitive shift in awareness known as the overview effect. Seeing our planet as a fragile, luminous blue marble, suspended in the vast darkness of space, with no visible borders or divisions, often instills a deep sense of the interconnectedness of all life, a profound appreciation for Earth's beauty and preciousness, and a renewed commitment to its stewardship. It is an experience that can transcend intellectual understanding, becoming a deeply emotional and spiritual realization. Could this perspective, writ large across a future spacefaring civilization, foster a greater sense of global unity and responsibility? But as we contemplate adapting to survive in these alien realms, we inevitably encounter deep ethical questions about adapting humanity itself. If the unyielding harshness of space demands more than our current biology can withstand, do we turn to genetic engineering to enhance radiation resistance, to modify our metabolism for different atmospheric compositions, or to reshape our physiology for different gravity wells? If we design artificial organs that function more efficiently in microgravity, or neural interfaces to augment cognitive function or mitigate psychological stress? At what point do these modifications begin to alter what it means to be human? Is such a transformation the ultimate expression of our adaptability, our ingenuity, our drive to survive and transcend limitations? Or is it a betrayal of our evolutionary heritage, a departure from the very nature that defines us, who decides what constitutes an acceptable alteration, and what are the potential unforeseen consequences of tinkering with the complex? Interconnected systems of human biology that have been refined over millions of years. The children born on Mars or in orbital habitats would know no other reality. Earth, for them, would be a story, a legend, a distant blue point of light in their sky. Their senses would be attuned to the engineered environment, their bodies perhaps subtly different, shaped by reduced gravity and a different sensory input. Would they feel a connection to Earth? Or would their primary loyalty be to their new off-world home? Would they still consider themselves human in the same way terrestrial humans do? Or would they represent the first generation of a new, post-Earth branch of humanity? The first true aliens of our own lineage. These are not merely speculative flights of fancy. They are fundamental questions that will confront us if we seriously pursue the dream of becoming a multi-planet species. The human element, in all its complexity, body, mind, and spirit, is both our greatest asset and our most vulnerable component in the quest to live beyond Earth. The void challenges not just our technology, but our very identity, forcing us to ask what we are willing to become in order to survive among the stars. The unseen universe and its silent questions. The cosmic stage upon which we aspire to enact our grand dramas of exploration and colonization is itself a realm of profound mystery, far stranger and more enigmatic than our everyday intuitions can readily grasp. Our comfortable narratives about the universe's origins and structure often mask deep uncertainties and unsettling paradoxes. Consider the Big Bang, that common shorthand for the universe's genesis. The term itself, coined somewhat derisively, conjures an image of a colossal explosion occurring at a single point in a pre-existing void. But the reality, as understood by modern cosmology, is far more nuanced and mind-bending. There was no sound, for there was no medium to carry it. More fundamentally, the Big Bang did not happen at a specific location in space. Rather, it happened everywhere, simultaneously. It was an expansion of space itself, not an explosion in space. In the earliest moments, the entire observable universe, with all its nascent matter and energy, was compressed into an unimaginably hot, dense state. Space itself was unfurling, like an infinite flower blooming from an infinitesimal seed. If the universe has no edge, as current observations suggest, then asking where the Big Bang occurred is akin to asking where on the surface of an expanding balloon its inflation began. The expansion is happening at every point on the surface. This understanding, however, leads to its own set of puzzles. One of the most significant is the horizon problem. When we look at the cosmic microwave background radiation, the faint afterglow of the Big Bang, an omnipresent whisper of microwaves filling all of space, we observe an astonishing uniformity in its temperature across the entire sky. Regions of the CMB that are on opposite sides of our observable universe, so far apart that light, traveling since the dawn of time, could not possibly have crossed the distance between them, nonetheless share almost precisely the same temperature, down to tiny fractions of a degree. How could these causally disconnected regions have reached thermal equilibrium if they never had a chance to interact, to exchange heat? It's like finding two cups of coffee, brewed in separate, sealed rooms miles apart, having cooled to exactly the same temperature without any communication. To resolve this and other cosmological conundrums, the theory of cosmic inflation was proposed. This theory posits that in the first fleeting fraction of a second after the Big Bang, a period almost unimaginably short, perhaps from 10 to the power of minus 36 seconds to 10 to the power of minus 32 seconds, the universe underwent a period of exponential superluminal expansion. It didn't break the cosmic speed limit by having matter travel faster than light through space, but rather by stretching the very fabric of space-time itself at an accelerated rate. During this inflationary epoch, a region smaller than a proton could have expanded to the size of a grapefruit almost instantaneously. This rapid stretching would have smoothed out any initial temperature variations, explaining the uniformity of the CMB, and also flattened the geometry of space to the near-perfect flatness we observe today. But inflation, while solving some problems, introduces new questions and even more astonishing possibilities. What triggered inflation? What caused it to stop so precisely, allowing for the more leisurely expansion that followed, which permitted stars and galaxies to form? And if inflation happened once, could it be a continuous process, happening in other regions of a much larger reality beyond our observable horizon? This leads to the concept of eternal inflation and the multiverse hypothesis, the idea that our entire observable universe might be just one bubble or pocket universe among an infinite or vastly numerous ensemble of other universes, each potentially born from its own inflationary event, and each perhaps with its own unique set of physical laws, fundamental constants, and even dimensionality. If this is true, then what we call the immutable laws of nature might be mere local ordinances, provincial rules that apply only within our specific cosmic neighborhood. Imagine the implications for future interstellar explorers. Reaching the edge of our bubble could mean encountering a boundary where our physics gives way to something utterly alien, rendering our technology useless and our very biology incoherent. The strangeness of the cosmic stage extends to its most fundamental constituents. We believe we understand matter, the solid stuff of tables, chairs, planets, and our own bodies. But delve into the quantum realm, and this familiar solidity dissolves. Atoms, once thought to be indivisible building blocks, were revealed to be mostly empty space. A hydrogen atom, for instance, is about 99.999996% void. If its nucleus were the size of a pea, its electron would orbit roughly a kilometer away. You, solid as you seem, are predominantly empty space, a fleeting configuration of quantum fields, a ghost made of mathematical patterns held together by forces we can describe with incredible precision, but whose ultimate nature remains elusive. And these fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, present their own cosmic puzzle. Why these four forces? Why do they possess their specific, measured strengths? The universe appears to be exquisitely fine-tuned for complexity and the emergence of life. If you were to alter the gravitational constant by even a tiny fraction, stars either could not form or would burn out too quickly. Adjust the strength of the strong nuclear force slightly, and the elements necessary for life, like carbon, could not be synthesized in stellar furnaces, or atomic nuclei would be unstable. Tweak the electromagnetic force, and the very chemistry upon which life depends would break down. This apparent fine-tuning is often referred to as the anthropic principle, the observation that the universe's fundamental constants and initial conditions seem to be precisely those required for conscious observers like ourselves to exist and observe it. Does this imply cosmic luck of an extraordinary degree? Are we living in a specially selected universe from a vast multiverse ensemble where most other bubble universes remain sterile and lifeless because their physical constants are not conducive to complexity? Or is there some deeper, yet undiscovered, physical principle at work that necessitates these specific values? The cosmic inventory grows curiouser still when we consider the dominant components of the universe: dark matter and dark energy. All the ordinary matter we can see and interact with, the stars, galaxies, planets, and ourselves, accounts for only about 5% of the total mass energy content of the universe. Approximately 27% is attributed to dark matter, an invisible substance that does not emit, absorb, or reflect light, interacting with ordinary matter only through gravity. Its presence is inferred from its gravitational effects on the rotation of galaxies and the bending of light from distant objects. Dark matter forms the invisible scaffolding around which galaxies coalesce and cosmic structures form, yet we do not know what it is made of. The remaining 68% of the universe is even more mysterious: dark energy. This is a hypothetical form of energy that permeates all of space and appears to be driving the accelerating expansion of the universe, pushing galaxies apart at an ever-increasing rate. Its nature is one of the biggest unsolved mysteries in physics. Think about that nearly 95% of our universe consists of substances and energies we cannot directly see, cannot touch, and barely understand. We are like explorers in the 16th century trying to map the globe with only 5% of its surface visible, navigating by the subtle effects of invisible currents and unknown landmasses. And it is into this vast, largely unknown ocean that we dream of launching our fragile colonial vessels. Amidst this cosmic grandeur and profound mystery, one observation stands out with unsettling clarity: the Great Silence. Our Milky Way galaxy alone contains an estimated 100 to 400 billion stars. Many, if not most, of these stars are likely to host planetary systems. Current estimates suggest there could be tens of billions of potentially habitable, Earth-sized planets in our galaxy. Given the age of the universe and the billions of years that many of these planets have existed under relatively stable conditions, it seems statistically probable that life should have arisen elsewhere, and that at least some of that life should have evolved intelligence and developed technological civilizations. Even if the emergence of such civilizations is exceedingly rare, say 1 in a billion suitable planets, There should still be thousands, if not tens of thousands, of spacefaring civilizations in our galaxy alone. Some of these would likely be far older and more advanced than our own. Yet, when we scan the skies with our radio telescopes, when we look for signs of astroengineering or interstellar travel, we find nothing. No unambiguous signals, no Dyson spheres, no evidence of galactic colonization. The galaxy appears hauntingly empty of the technological signatures we might expect. This is the Fermi paradox. Where is everybody? The silence is profound and deeply unsettling. Does it mean that life itself is incredibly rare? Or that the transition to intelligence is a major bottleneck? Perhaps technological civilizations invariably self-destruct before they can achieve interstellar travel. Or maybe the challenges of living beyond one's home planet, the very challenges we are contemplating, are so immense that they represent an insurmountable great filter that silences countless emerging civilizations before they can announce their presence to the cosmos. Or a more solitary thought. Perhaps we are truly among the first, or even the only, technological species to emerge in our galactic neighborhood. The unseen universe, with its hidden constituents, its mind-bending origins, and its deafening silence, poses not just scientific questions, but deep existential ones, casting a long shadow of uncertainty over humanity's ambitious dreams of cosmic expansion. The indifferent stage in humanity's uncertain future. The universe, for all its breathtaking beauty and intricate laws, operates with a profound and chilling indifference to the aspirations, struggles, and very existence of conscious beings like ourselves. There is no inherent morality woven into the fabric of space-time, no cosmic justice ensuring the triumph of good over evil, and certainly no special concern for the survival or extinction of Homo sapiens. Stars explode as supernovae, sterilizing any nearby planetary systems with lethal radiation, not out of malice, but because their core chemistry dictates it. Asteroids and comets, remnants from the solar system's formation, drift through space on gravitational tides, occasionally impacting planets and potentially ending billions of years of evolutionary progress in a geological instant, as one likely did for the dinosaurs. Gamma-ray bursts, the most powerful explosion in the universe, can erupt from distant galaxies, sending focused beams of high-energy radiation across intergalactic space, capable of stripping atmospheres and causing mass extinctions on any unprotected worlds in their path. These are not targeted assaults, they are merely the impersonal workings of cosmic mechanics. In this indifferent cosmos, any human presence beyond Earth would exist solely because we, through immense effort and continuous technological intervention, create and meticulously maintain the conditions for it. There is no natural, welcoming niche for humans anywhere but Earth. Every off-world habitat, every lunar base, every Martian colony, every generation starship would be a fragile, artificial island of habitability in a vast, encompassing ocean of lethality. Survival would depend entirely on the flawless, perpetual functioning of life support systems, radiation shielding, atmospheric containment, and resource recycling. This creates a fundamental contradiction at the heart of the space colonization dream we seek to expand human presence into a cosmos that is inherently hostile to that presence. We attempt to create persistence in an environment characterized by impermanence and entropy. We strive for safety and stability in a universe defined by cataclysmic violence and unpredictable danger. The challenge of replicating Earth's complex, self-regulating ecological systems, which took those 4.5 billion years to evolve their intricate web of interdependencies. Within the confines of an artificial habitat is perhaps the most daunting technological hurdle of all. Consider Earth's biosphere. It's not just a collection of organisms, but a dynamic system of interlocking cycles: the carbon cycle, the nitrogen cycle, the water cycle, the oxygen cycle, the rock cycle, all operating on planetary scales and over geological timescales to maintain a relatively stable environment conducive to complex life. The oxygen we breathe is not a permanent feature of our atmosphere. It is actively produced and maintained primarily by photosynthetic life, from rainforests to phytoplankton in the oceans. Without this continuous biological activity, atmospheric oxygen would gradually deplete as it reacted with minerals on the Earth's surface. To sustain human life in a closed habitat on Mars or in deep space, this entire planetary-scale life support machinery must be replicated, miniaturized, and managed with near-perfect efficiency and reliability. Every breath of air, every drop of water, every calorie of food, and every waste product must be meticulously accounted for, processed, recycled, and reintegrated into the system. The margin for error would be vanishingly small. A significant failure in the air revitalization system, the water reclamation process, or the food production units could lead to catastrophic consequences within hours or days. Earth's biosphere possesses enormous redundancy and resilience. If one ecosystem is damaged, others can often compensate. If one species goes extinct, others may evolve to fill its ecological niche. This robustness is the product of billions of years of evolutionary trial and error. Space habitats, by contrast, would likely be far less resilient, designed from first principles with a limited number of species and carefully engineered pathways, the most ambitious attempt to create a large-scale and materially closed ecological system on Earth. Biosphere 2 in Arizona during the early 1990s serves as a stark cautionary tale. Despite significant funding and scientific expertise, the 2-year experiment encountered numerous problems. Oxygen levels dropped to dangerously low concentrations. Many of the introduced pollinating insects died off. Most vertebrate species went extinct. Crop yields were insufficient to feed the 8 human inhabitants, and the crew themselves experienced interpersonal conflicts and factionalism. And this occurred on Earth, with access to external resources, sunlight unattenuated by vast distances, and the planet's natural gravity and magnetic field. Replicating such a system with even greater reliability, for indefinite periods, millions of miles from Earth, is a challenge of an entirely different magnitude. The perpetual reliance on fallible, human-made technology for every aspect of survival would create an immense and unceasing psychological burden for colonists. They would live with a constant awareness that their existence hangs by the thinnest of technological threads, that a critical system failure, a micrometeoroid puncture, or even a human error could spell swift annihilation. This is a stark contrast to life on Earth, where even if our technologies fail, the underlying environment generally remains habitable, offering a natural safety net. In space, there is no such fallback. Technological regression that might cause hardship or societal decline on Earth would mean certain extinction for an off-world colony. Furthermore, the tyranny of distance, as discussed earlier, would have profound long-term consequences for the human species if we were to successfully establish multiple isolated colonies. Communication delays measured in minutes, hours, or even years for interstellar settlements would make real-time interaction impossible. This would inevitably lead to cultural divergence. Different colonies, facing unique environmental challenges and developing under conditions of extreme isolation, would likely evolve distinct languages, social structures, values, and even mythologies. Over many generations, subjected to different gravitational fields, radiation levels, and perhaps even deliberate genetic modifications, biological divergence could also occur, potentially leading to the splintering of Homo sapiens into new distinct species, no longer able to interbreed or perhaps even to fully understand one another. Is this cosmic diaspora the grand destiny of intelligence, to diversify and fill every available niche? Or does it represent a tragic fragmentation, a loss of shared human identity? The universe, in its cosmic indifference, sets the stage but offers no script. It provides the raw materials, the elements forged in stars, but no guarantees of success or even survival. Is our relentless drive to expand beyond Earth, to push against these seemingly insurmountable obstacles, a testament to a uniquely human capacity for transcendence, an expression of our deepest exploratory instincts? Or is it a form of collective hubris, a refusal to accept our inherent biological limitations and our profound dependence on our home planet? Perhaps it is a mixture of both. The history of life on Earth is a history of adaptation, of overcoming environmental challenges, of radiating into new niches. The transition from aquatic to terrestrial life was an epochal leap, fraught with peril for the pioneering organisms. Is the transition from planetary to interplanetary, and eventually interstellar, existence simply the next great evolutionary hurdle? As we stand at this crossroads, a species capable of dreaming of the stars but not yet truly capable of inhabiting them sustainably, we must confront these deep contradictions. The impossible challenge of living beyond Earth forces us to question not just our technological prowess, but the very essence of what it means to be human. What values do we prioritize? What aspects of our terrestrial heritage are essential to carry forward into the void? And what might we need to leave behind or transform in order to survive the long-term fate of Earth itself? And our Sun adds another layer to this existential calculus. Our planet will not remain habitable forever. In about 1 billion years, the gradually brightening Sun will likely make Earth too hot for complex life. In about 5 billion years, the Sun will exhaust its core hydrogen fuel and expand into a red giant, potentially engulfing the inner planets, including our own. On the longest of cosmic timescales, even the universe itself has a finite lifespan of productive activity, with star formation eventually ceasing and matter itself perhaps decaying into a cold, dark, empty expanse. Against this backdrop of ultimate cosmic transience, the drive to spread life and consciousness beyond our single, vulnerable world takes on a different, perhaps more urgent, meaning. If consciousness is a rare and precious phenomenon in the universe, then perhaps ensuring its long-term survival, beyond the lifespan of a single planet or star, is a moral imperative, a responsibility we owe not just to ourselves, but to the cosmos itself. The stars watch in silent indifference, their light traversing eons to reach our eyes. They have witnessed the rise and fall of countless worlds, countless possibilities. Our future among them remains unwritten, a narrative we are only just beginning to compose, fraught with peril, yet gleaming with the audacious hope that defines our species. The impossible challenge awaits, and with it, the potential for a transformation far more profound than simply changing our address in the cosmos. It is a challenge to redefine our place in the universe and, in doing so, to discover what humanity might yet become. The journey to the stars, as we have seen, is not a simple extension of our terrestrial adventures. It is a confrontation with the deepest truths of our existence, our profound biological connection to Earth, the staggering scale and indifference of the cosmos, and the inherent fragility of life and consciousness. The universe presents us with a fundamental paradox. It is the crucible that forged us, yet it is also an environment that actively seeks to unmake us the moment we step beyond our planetary cradle. Every law of physics, every biological imperative, every psychological reality seems to underscore the immense, perhaps insurmountable, difficulty of truly making a home beyond Earth. Yet, in the face of these overwhelming challenges, humanity continues to dream, to design, to reach outward. Is this mere folly, a species-level hubris refusing to acknowledge its limits? Or is it something more profound, an intrinsic characteristic of consciousness itself, to question, to explore, to strive to transcend its apparent boundaries? Perhaps our destiny is not to find easy answers or comfortable new homes, but to engage with these impossible questions, to push against the very fabric of what seems possible. In doing so, we learn more about the universe, but more importantly, we learn more about ourselves. The silence of the cosmos, the vast distances, the lethal environments, these are not just obstacles, they are mirrors reflecting our own vulnerabilities, our courage, our ingenuity, and our deepest fears. The attempt to live beyond Earth, whether it ultimately succeeds on a grand scale or remains a series of heroic but limited forays, will inevitably change us. It forces us to consider what aspects of humanity are truly essential, what we must carry with us to the stars, and what we might be willing to transform or even sacrifice. The stars will continue their silent vigil, indifferent to our triumphs or failures. Earth will continue its cosmic journey, a tiny oasis of life in an ocean of desolation. But the questions raised by our celestial ambitions will linger in the human spirit. What is our purpose in this vast, unfeeling universe? Are we merely a fleeting biological accident on a minor planet? Or are we the means by which the cosmos becomes aware of itself, a conduit for consciousness to spread, and perhaps, in some distant future, to comprehend the totality of its own existence? The path ahead is shrouded in uncertainty. There are no guarantees. But the human story has always been one of facing the unknown, of stepping into the darkness armed with little more than curiosity, determination, and the audacious hope that beyond the horizon lies something worth discovering. The impossible challenge of living beyond Earth may be the ultimate expression of this enduring human spirit, a testament to our refusal to simply accept the world as it is, and our unyielding desire to imagine and strive for what it might yet become. The cosmos waits. And we, children of Earth, stand at the edge, looking out.
When scientists of the 17th and 18th centuries were studying historical records of eclipses, including information dating back thousands of years, which became accessible thanks to astronomers at the Chinese imperial court, they noticed an intriguing pattern. Their calculations and observations didn't align with the ancient sages' records. The calculated dates of ancient eclipses didn't match up with historical chronicles. As they delved deeper into the past, the discrepancies became more significant, and the intervals between eclipses grew longer. This discrepancy became evident when examining the history of these phenomena over thousands of years. What was happening was that the rotation of the Earth was slowing down. Perhaps the Moon was moving away. It would take future generations of astronomers and physicists to piece together this puzzle and discover that the Earth's rotation was indeed slowing down, and the Moon was gradually moving away. But what connects these processes? Let's find out together. But first, let's recall what we know about the Moon. The Moon is Earth's only natural satellite. According to the most popular theory among scientists, sometime after the Earth's formation, a celestial body the size of a planet collided with it at a tangent. As a result of this impact, some of the material from this object and part of the Earth's mantle were ejected into orbit around the Earth. This eventually formed the Moon, which began to orbit at a radius of about 60,000 kilometers. The study of the Moon's gravitational field, internal structure, and the reconstruction of its thermal history has revealed the presence of both a solid inner core and an outer metallic core within the Moon. The Moon has a very weak magnetic field, generated by residual magnetism in lunar rocks and the tidal forces acting on its core. The key mystery behind the Moon's gradual drift away from Earth lies in tidal acceleration. This is an effect caused by gravitational interactions in a natural satellite central body system. The primary consequences of this effect are changes in the satellite's orbit and alterations in the central body's rotation about its axis, as observed in the Earth-Moon system. Another consequence is the heating of a planet's interior, which is believed to have had a significant impact on Earth's past. The Moon has been orbiting Earth for the past 4.5 billion years. Due to Earth's greater mass, it exerts a much stronger gravitational force on the Moon than the Moon does on Earth. This means it pulls the Moon towards itself more strongly. This results in tidal forces that cause tides in our oceans. Gravitational attraction between the Moon and Earth is stronger on the side of Earth facing the Moon. This force is strongest in the region closest to the Moon. As a result, the Moon slightly pulls the equatorial regions of Earth towards itself. This significant gravitational pull of the Moon causes high tides in the ocean waters in this region, creating a bulge on the Earth's surface known as the equatorial bulge or tidal bulge. Both sides of the Earth experience this effect, much like how our planet experiences a bulge due to the Moon's gravitational pull. The Moon also experiences a tidal bulge on the side closest to Earth, and this is where we come close to the question of why the Moon is actually moving away from Earth. In reality, there is nothing supernatural about this. It's the nature of both Earth and the Moon to age, and many things change. For example, around 620 million years ago, Earth's days were only 21 hours long, but gradually, days became longer by about 1/500th of a second per century due to the gravitational forces between Earth and the Moon. These forces, along with lunar tides, slow down Earth's rotation. However, due to the conservation of angular momentum for both celestial bodies, the Moon, in turn, begins to rotate faster and move into wider orbits. Will there ever be a moment when our natural satellite disappears into the depths of the universe? Perhaps, but not until about 4.5 billion years from now, when our Sun starts to fade and becomes a red giant. However, there's another scenario to consider. We now know that since its formation, the Moon has been gradually moving away from our planet. The rate of this movement has been increasing and is currently about 3.8 centimeters per year. If this continues, you might wonder how the Moon could ever fall to Earth. Believe it or not, some scientists believe this scenario is possible, though fortunately, it won't happen anytime soon. A few years ago, American planetary scientist Jason Barnes stated that the Moon could collide with Earth in about 6.5 billion years. He explained this by suggesting that by that time, Earth's rotational speed would significantly slow down. According to various estimates, this could happen in approximately 50 billion years when celestial bodies reach a mutual spin-orbital resonance. As a result, the Moon would not move away, but would be drawn closer to our planet. Interestingly, our Sun might play a role in this. Approximately 5 billion years from now, our Sun will deplete its hydrogen, which is its source of energy. It will enter a new phase of its evolution, becoming a red giant. The star's luminosity will increase, internal pressure will rise, and its outer shell will expand. Powerful outbursts from the red giant's atmosphere could quickly alter the Moon's orbit, causing it to slowly move toward Earth. But will there be a collision? If you're thinking of a head-on collision, that's not the case. When the distance between the Moon and Earth decreases to about 18,000 kilometers, the Roche limit, tidal interactions will tear the Moon apart into a massive pile of debris. Some of this debris will form a system of rings around Earth. Over time, most of the rings will disintegrate, and the remnants will collide with Earth. In any case, by that time, life on Earth will be impossible, just as it will be on any other planet in the solar system. When the Sun transforms into a red giant, the star's atmosphere will expand so much that it could reach the current orbit of Earth. Of course, before this happens, the two planets closest to the Sun, Mercury and Venus, will be completely destroyed. Let's exclude the presence of a red giant from this chain of events. In such a case, How would it affect Earth? The disappearance of the moon would have a significant impact. Although the moon's influence on stabilizing the Earth's axis of rotation is somewhat exaggerated, this influence is undeniable. It was previously believed that if the moon disappeared, the Earth's axial rotation would become completely chaotic. This would manifest in unpredictable changes in seasons. The disappearance of the moon would also greatly affect many species of animals and plants, especially those whose life cycles are somehow linked to tides and tidal patterns. Without the moon, there would be no eclipses, and there would be no object capable of partially blocking the sun's disk. It's worth noting that nights would become darker. You might ask, will the moon eventually drift away from Earth? The moon is gradually moving away from Earth, taking some of Earth's rotational energy with it as it rises in its orbit. The moon's gravitational pull is slowing down Earth's rotation, causing Earth to spin more slowly around its axis. Eventually, the moon will reach a geostationary orbit where the satellite's speed over the planet matches Earth's rotation speed. The moon will be in a geostationary orbit, and a phenomenon known as tidal locking will occur. This means that the moon and Earth will always face each other with the same sides. This is a stable state, and it will continue for billions of years. Only in the very distant future, the influence of our sun or some other object might disrupt the mutual rotation of the Earth-Moon pair, and the moon could fall to Earth. No scientist can accurately say what would happen if the moon disappeared. Of course, it could be blown up, move away from the planet, or anything else might occur. The only thing known for sure is that the planet's climate would change, and the conditions for life could worsen. After all, our tandem has existed for so many years. But before that happens, a lot of time must pass, so we are unlikely to know the answer to this question. So in general, there's no need to worry, unless people themselves want to accelerate these processes. The sun's rays penetrated reluctantly through the windows of the dwelling. Having just woken up, he walked over to the window, enjoying the planet bathed in sunlight. "Time to go," he mumbled, putting on his spacesuit and locking the door, heading out for his lunar duties. What is this? Where am I, really? He wondered. It felt like the beginning of a fantastic movie. Oh no, what if, in 100 to 200 years or more, people will be living on the moon just like they do on Earth now? After all, there are already many lunar missions being planned, but more on that later. Let's first remember what this celestial body is and why we haven't been going there for sightseeing, considering that humans have already set foot on the moon. Let's start by recalling how human exploration of the moon began. Humanity began studying the moon more than 2,200 years ago, back in the 3rd century BC. Aristarchus, a Greek, made an approximate measurement of the moon's size in the early 17th century. Galileo observed the moon's mountains and craters through his telescope. From the 1950s, the space age began, and the moon became the first celestial body beyond Earth that humans attempted to reach. Since then, more than 100 robotic explorers from over half a dozen countries have sent spacecraft to the moon. 9 manned missions completed round-trip journeys to the moon and back. The moon was first visited by unmanned Soviet spacecraft Lunar 1 and Lunar 2 in 1959. As of April 2019, 7 countries have achieved the first human landing on the moon, which occurred on July 20, 1969, during the Apollo mission in 1969 to 1972. 12 American astronauts walked on the moon and used lunar rovers to travel its surface, expanding their scientific research. The Apollo astronauts brought back 382 kilograms, 842 pounds, of rock and soil for analysis. Then, the United States followed up with 9 NASA Ranger spacecraft, launched between 1961 and 1965, which provided scientists with close-up photographs of the moon's surface. The Ranger missions were bold, one-shot affairs. Each spacecraft was designed to fly to the moon and take as many pictures as possible before crashing onto its surface. By 1965, the imagery from all the Ranger missions, particularly Ranger 9, provided detailed information about lunar terrain and potential landing hazards for future human missions. Each mission after Apollo 11 marked milestones in space travel and lunar exploration. 4 months after the first human moon landing, Apollo 12 achieved a much more precise lunar landing. Apollo 13 narrowly avoided a disaster in April 1970 when onboard oxygen tanks exploded, forcing the crew to abort their planned lunar landing. All three astronauts survived. In January 1971, the commander of Apollo 14, Alan Shepard, set a new record for the farthest flight on the moon, 9,000 feet. He even threw a few golf balls into the nearest crater using a homemade 6-iron. Apollo 15, launched in July 1971, was the first of 3 missions capable of longer stays on the moon, spending 3 days on its surface. They managed to collect hundreds of pounds of lunar samples and traveled over 17 miles on the first manned lunar rover. The Soviet Union sent the remotely controlled lunar rover, Lunokhod-1, to the moon in 1970. Apollo 16 in 1972 and Apollo 17 in 1972 were the last 2 manned lunar missions. Meanwhile, the Russian spacecraft Luna 24, launched unmanned in 1976, became the last mission to land on the moon until the next century. The samples collected during these lunar explorations provided a wealth of knowledge about the geology and formation of the moon. After the dramatic achievements of the 1960s and 1970s, major space agencies shifted their focus to other objects for several decades. Currently, we have 3 robotic spacecraft and an upcoming lunar reconnaissance orbiter and dual spacecraft missions planned for the moon. Now let's talk about what's planned for the near future, with the most promising program, in my opinion, being Artemis. NASA introduced the Artemis program in 2019. According to this program, the heavy-lift rocket SLS, Space Launch System, will transport astronauts to the moon by no later than 2024. The program consists of 2 phases. The first phase involves landing American explorers near the South Pole, where deposits of water ice are located. The second phase aims to establish a continuous presence of astronauts on the lunar surface. Russia, through Roscosmos, plans to resume its lunar program in 2021. They intend to test 2 new rockets this year. The Russian lunar program will be implemented in several stages, extending until 2040. The primary goal is to develop all the necessary technologies, such as creating a lunar station's core module and testing the piloted Federation spacecraft. The second stage involves testing means of access to the lunar surface and conducting the first piloted test flights. In the third stage, the construction of a Russian lunar base should be completed, planned between 2030 and 2035, with astronauts spending at least 2 weeks on the moon. China, of course, couldn't be left behind. This country is determined not to fall behind its competitors, aiming to become a space superpower. Last year, it sent the Tianfu spacecraft, which successfully landed on the moon's surface. This news created quite a stir. Currently, China is preparing its Chang'e 5 lunar rover. When it will be launched and the specific stages of the program's implementation are still unknown, but its mission is to collect lunar soil samples weighing up to 2 kilograms for further study. China appears to be positioning itself to win the new lunar race, surpassing the USA and Russia. Since 2013, the Chinese have been developing the Long March 9, a super-heavy rocket. Periodically, information emerges from China about a landing module for a crewed spacecraft. Other spacefaring nations also want to join the race, including European countries, India and Japan. India is working independently, while Japan and Europe are collaborating on joint programs. Why does humanity show such interest in this lifeless, rocky desert called the moon? Today, many companies are highly interested in lunar tourism, while others aim to extract resources from the moon. A third perspective sees the moon as a potential new home for humanity. The Israeli team at Space IL, for instance, has a small probe with the primary goal of inspiring young Israelis worldwide. This landing is meant to motivate a new generation of engineers and scientists who will develop technologies for space exploration. Many hope that in the future, countries can use the moon as a kind of launching pad for further planetary conquest, such as Mars. By utilizing lunar resources, groups of scientists could extract materials for rocket fuel, enabling journeys to planets that were previously out of reach. This is the vision of Robert Bigelow, the founder of Bigelow Aerospace. His company is focused on creating a lunar base and its development. The moon could also serve as a testing ground for missions to more distant places in the solar system. According to Bigelow, his company might require a significant number of astronauts who will ensure the functionality of these missions, introduce innovations into space equipment, inform the public, and much more. Bigelow hopes this could become a reality within the next 10 years. However, the question arises, can different countries cooperate on the moon without conflicts? According to Bigelow, our history hardly contains cases of peaceful coexistence. That's why humanity needs to become wiser and resolve all conflicts on Earth. Transferring them to the moon would require developing an entirely new level of mutual respect and relations. Regarding the exploration of outer space, all states and private organizations will have to agree on and establish common rules to regulate who has the right to claim a specific area of the lunar surface do not exist at present. According to the 1967 UN treaty signed by 128 countries, no one can own a piece of the moon. What kind of relationship awaits us with the moon in the future, and will we be able to visit it for recreational purposes? Time will tell. Could the moon be an artificial object? In today's space journey, we will travel not too far from our planet, almost like a weekend getaway to the moon. However, we won't be discussing the standard set of information about it. Instead, we'll contemplate the idea. What if the moon has an artificial origin? Some conspiracy enthusiasts might exclaim, "Finally!" But that's not how astronomers, who observe it closely, see it. We love science because it allows us to test and either confirm or debunk hypotheses. So put on your spacesuits and let's embark on an exploration of the moon. There are several theories about the moon's formation, but the most widely accepted one is the collision hypothesis. According to this hypothesis, in the early history of the solar system, a protoplanet about the size of Mars collided with Earth. Some variations of this theory suggest that this protoplanet was named Theia. The collision resulted in lighter materials being ejected into space, forming the moon, as well as the creation of the asteroid belt. This hypothesis is supported by observations of the moon's chemical composition, which is nearly identical to Earth's, indicating a common origin. Additionally, the moon orbits Earth at a relatively close distance, suggesting it formed in proximity to our planet. While the collision hypothesis is widely accepted, it continues to undergo scientific research and debate. The moon's origin has long intrigued scientists. Back in the 1960s, Soviet researchers Mikhail Vasin and Alexander Sherbakov proposed a hypothesis suggesting that the moon is too large to be a natural planetary satellite. Its size is roughly 1/3 of Earth's, while satellites of other planets are much smaller in comparison to their hosts. There are also some other intriguing features about the moon. For example, only from Earth can we witness a total solar eclipse, where Earth, the moon, and the sun are positioned at just the right distances to allow the moon to completely cover the sun periodically. If the moon were either closer or farther from Earth, we would not observe this phenomenon in the same way. It's hard to shake the thought that all of this was created deliberately. But who and why created it? Where did such precision in the orbits of Earth, the moon, and the sun come from? They seem elegantly arranged, as if by a cosmic engineer. If our planet were slightly closer or farther from the sun, we would never see these beautiful celestial phenomena. Not to mention that the moon directly regulates the tides on our planet, impacting the life cycles of all Earth's creatures, including humans. The analysis of lunar soil collected by rovers has shown that it appears to be magnetized, even though the moon lacks its own magnetic field. What's intriguing is the suggestion that the moon may be older, not only than Earth, but also than the sun itself. Some propose that the moon appeared in our sky relatively recently. Some conspiracy theorists suggest analyzing the legends and myths of various ancient civilizations to find accounts of times when there was no moon in the sky, followed by its sudden appearance. In fact, there are legends of 2 moons, but one supposedly disappeared. Lunar craters have nearly uniform depths, indicating that meteorites that impacted the surface encountered some kind of resistance, likely a metallic shell. On Earth, similar metallic shells are used to make submarine hulls. This suggests that the moon has a very solid shell. When the moon's density was measured, it turned out to be surprisingly low, much lower than Earth's. This led to the speculation that the moon might be hollow inside. Many experiments have supported the idea that there are massive metal masses hidden within the moon's core. All of this has led scientists to consider the possibility that our moon is actually an abandoned spacecraft or a discarded extraterrestrial base station. However, there's another theory. This spacecraft is ancient, but still operational. In 1969, when a NASA spacecraft crashed on the moon, it vibrated like a bell for an hour, emitting seismic activity. This incident puzzled scientists, and they began to wonder why such an event occurred. By all calculations, the answer could be one: if the moon is hollow inside. However, natural celestial bodies cannot have such large voids. Either errors were made in the calculations, or Earth's satellite was artificially constructed. Over the next 3 years, leading researchers at NASA tried to find flaws in the initial assessments, but found no faults. The only working theory that emerged was that the moon might be an artificial creation. Lunar soil brought back to Earth was studied in 6 laboratories, and what astonished scientists was the composition of the moon's rocks. They contained titanium and minerals with similar characteristics to those on Earth. This composition contributes to the moon's incredible strength. Additionally, the presence of creep rocks in lunar soil, rich in so-called incompatible elements that accumulate in the liquid phase during magma crystallization, was notable. It also contained heat-producing elements, including radioactive uranium, thorium, and the radioactive isotope potassium-40. All of this further supported the hypothesis of the moon's artificial origin. Furthermore, it became clear that the Earth's satellite must be hollow inside. There should be vast cavities beneath the solid surface. Otherwise, the vibrations resulting from the relatively weak crash of the NASA satellite would not have been as prolonged and powerful. Astronomers from the USSR and France who became interested in the moon's origin proposed a hypothesis that it's not just an artificial satellite, but a colossal installation of an unknown civilization. Natural satellites should have much smaller radii than the moon, according to their calculations. In 2002, NASA's website published findings that supported the assumptions made 20 years earlier, suggesting that the moon is an exception to the rules. But what about the fragile regolith? For decades, there have been reports of an extremely lightweight and fragile lunar soil. However, there's a hypothesis that this is actually settled cosmic dust, and the real lunar soil is an incredibly robust alloy of titanium and minerals. Hundreds of thousands of years ago, Earth's satellite was a perfectly spherical body, which over millennia has transformed into a cratered celestial object. Speaking of craters, they also emphasize this hypothesis. Their diameters vary from a few meters to several kilometers, yet they all have roughly the same depth. This is unusual because larger meteorites should create wider and deeper craters. This rule only partially applies, mainly to those meteorites that left astroblames with diameters greater than a kilometer, indicating that a colossal impact occurred. Even in these cases, the crater depth reaches only about 8 kilometers, with a diameter of 2,200 kilometers. This once again underscores the fact that the lunar soil is incredibly sturdy, preventing the Earth satellite from breaking apart upon the impact of such a massive celestial body. In 2009, research conducted by American scientists revealed that the lunar surface consists of 2 layers of substances: a less durable outer layer, about 6 kilometers thick at the poles, and a more durable layer about 25 kilometers thick, known as the dark armor. In nature, substances can undergo diffusion. In such cases, a transitional layer is created when 2 substances react and mix. However, on the moon, there's no such observed transition. It's as if there are 2 distinct layers with a clear boundary. Unfortunately, modern technology doesn't allow us to determine what lies beneath the dark armor. So, for now, the tinfoil hats can be set aside. Meanwhile, French scientists combined available data and computer modeling to ascertain what lies beneath the lunar surface. To understand the moon's structure, the composition of Earth and other celestial bodies, astronomers have to rely on data from seismic activity. How acoustic waves created by surface vibrations travel through and reflect off the material inside the planet or moon helps scientists create a detailed map of the object's interior. However, there's a problem when it comes to the moon. Due to the Apollo missions, we do have seismic activity data, but the resolution is too low to precisely determine the composition of the lunar core. It is assumed that a liquid outer core surrounds the solid inner core, but this hasn't been definitively proven. According to research published in the journal Nature, astronomers from the French National Center for Scientific Research used known facts to create a profile of the moon's characteristics. These included the extent of its deformation due to gravitational interaction with Earth, variations in distance from Earth, and density. They conducted modeling with various core materials to find a model that matched observational data. They found that the lunar core should closely resemble that of Earth, with an outer liquid layer and a solid inner core. According to their modeling, the outer core has a radius of approximately 362 kilometers, and the inner core is about 258 kilometers. This accounts for about 15% of the moon's total radius. The inner core, as discovered by the team, also has a density of about 782 kilograms per cubic meter, very close to the density of iron. Thus, scientists were able to confirm earlier hypotheses about a lunar core similar to Earth's. Further exploration of the satellite will help us learn more about its history and the disappearance of magnetic fields. Such a magnetic field is sustained by motion and convection in the core, so what makes up the lunar core is directly related to how and why the magnetic field disappeared. Considering humanity's hope to return to the moon in the relatively near future, we may have to wait for seismic confirmation of these discoveries. In the meantime, representatives of different countries are debating the rules for exploring the closest planets in the solar system. Ownership of lunar land. Certificates for lunar land parcels are being sold online, and while such purchases are not widespread, they are in demand. Experts continue to debate the legal validity of such private property deals on other planets and their satellites. Outer space, including the moon and other celestial bodies, is not subject to national appropriation, whether through claims of sovereignty or any other means. This is stated in the second article of the Outer Space Treaty, signed by more than 100 countries worldwide in 1967. However, even if we were to acknowledge that private individuals and companies can own land on the moon, the question remains: who can rightfully claim such ownership? According to the claims of the Lunar Embassy itself, more than 6 million people have purchased lunar land through them. By 2013, the company had earned about $11 million from these sales. And while more recent data isn't available, it's likely that this sum hasn't significantly increased as the trend for such purchases has waned. Prices for lunar land parcels on the Lunar MBC website range from $25 for approximately 40 acres to $500, as the saying goes, there's no smoke without fire. After comparing data obtained using mini-RF with maps of metal oxide concentrations made with a wide-angle camera LROU, scientists confirmed that larger craters with higher dielectric properties are directly related to the concentration of these metallic minerals. While the first few hundred meters below the silvery lunar surface may lack any precious metals, the deeper you go, the more valuable metals there are. These discoveries bolster NASA's mission. The Laboratory for Restoring Gravity and Internal Affairs, which found a mass of metals 5 times greater than the large island of Hawaii beneath the South Pole Aitken Basin, says these mini-RF data are invaluable. They not only continues to provide data on what might be hiding on the surface of the moon and beneath it, but also sheds light on how it formed and what its true celestial connection with Earth might be. The race to attract wealthy clients into space continues, but the race for mining valuable minerals on the moon is just beginning. The most interesting moons in the solar system. It's hard to imagine our night sky without the moon. Some compare it to a cheese wheel, others see an unassuming face observing nighttime life, while to some, it simply lights the evening path. The moon is the first planet's satellite closest to the sun. Our neighbors Mercury and Venus move through space without having a single satellite, but Mars, on the other hand, can boast of having 2 natural satellites. Beyond that, just imagine, in 2019, astronomers discovered 20 new satellites of Saturn, making it the record holder in the solar system for the number of known satellites with a total of 82. That's some busy traffic. Yet they say space is nothing but emptiness. The other planets in our system also have dozens of satellites each. However, today we would like to find out which of these moons can be called the most interesting, so let's find out. Ganymede. Ganymede is the largest moon in the solar system, and it orbits Jupiter. It even has its magnetic field. Its diameter is 5,268 kilometers, which is 8% larger than that of Mercury. However, its mass is only 45% of Mercury's mass. But among planetary satellites, it's exceptionally large. Ganymede exceeds the moon in mass by 2.2 times. Interestingly, it's quite fitting for its owner, Jupiter. This moon was discovered by Galileo Galilei, and its name was given by another astronomer, Simon Marius, in honor of Ganymede, the cupbearer at the feasts of Zeus. By the way, Marius gave names to some other moons as well. Thanks to him, the names of heroes from ancient mythology became widespread in the newly discovered world of moons. In common language, sometimes satellites are also called moons. Some consider Titan, Saturn's moon, to be the most promising celestial body for colonization, rather than Mars. It has a dense atmosphere, 1/3 denser than Earth's, and it likely has water from which oxygen can be obtained. This atmosphere effectively shields it from cosmic radiation. Moreover, Titan is the only celestial body besides Earth where the existence of liquid on the surface has been proven. The downside is the local atmosphere consists mainly of methane and other inhospitable gases. Also, it's very cold, about minus 180 degrees Celsius. Jupiter's second largest moon, and one of the 4 Galilean moons, is Callisto, the most distant from the planet. It is the 3rd largest moon in the solar system, following Ganymede and Titan. Callisto's diameter is approximately 99% of Mercury's diameter. It was discovered in 1610 by Galileo Galilei, and was named according to the tradition after a character in ancient Greek mythology, Callisto, who was a lover of Zeus. Nevertheless, Callisto is not the most picturesque object in our system. It is known for having the most craters covering almost its entire surface. There is no geological activity on Callisto, so its terrain remains unsmoothed. Io, one of Jupiter's moons, is the most geologically active body in the solar system. It has over 400 active volcanoes on its surface. Some of these volcanoes have eruptions so powerful that they reach heights of 500 kilometers. Io is primarily composed of silicate rock surrounding a molten core of iron or sulfur. Most of its surface consists of plains covered in sulfur or frozen sulfur dioxide. However, on the moon's surface, you can also observe over 100 mountains that have formed from the moon's crust. Some of these peaks are higher than Mount Everest on Earth. The only known moon that rotates in the opposite direction to its planet is Triton, a moon of Neptune. Triton is one of the few geologically active moons in the solar system, and its complex geological history is evidenced by tectonic activity, intricate terrain, and numerous cryovolcanoes. The average surface temperature of Triton is minus 235 degrees Celsius, making it so cold that nitrogen likely settles on its surface as frost or snow. Triton is believed to be the coldest geologically active object in the solar system. Miranda is a moon of Uranus, and it experiences unique seasonal changes. Each pole of this moon is in complete darkness for 42 years, followed by 42 continuous years of illumination. Miranda possesses a highly diverse surface with various features, including fissures, rifts, valleys, craters, ridges, depressions, and terraces. Its surface appears as though it has been slashed, and it contains the deepest canyons in the solar system, several times deeper than Earth's deepest canyons. Charon, the moon of the dwarf planet Pluto, has a diameter of approximately 1,200 kilometers. In 2006, there was a proposal to classify Charon as a planet, which would have made the Pluto-Charon system a double planet. However, the final resolution introduced the concept of a dwarf planet, and Pluto was classified as such, while Charon remained classified as a moon. In July 2015, NASA's New Horizons spacecraft reached Pluto and Charon, marking the first time in history that they were explored. The spacecraft followed a flyby trajectory and captured images of both sides of Pluto, although the images taken before the flyby have lower resolution. From the images, it is clear that Charon is noticeably darker than Pluto, suggesting that these objects significantly differ in composition. While Pluto's surface contains a lot of nitrogen ice, Charon is covered in water ice, and its surface exhibits a more neutral, less reddish color. Saturn's moon Iapetus features a unique mountainous ridge encircling its equator. This ridge reaches heights of 13 kilometers and has a width of 20 kilometers. Interestingly, Iapetus's leading hemisphere is as dark as soot, while its trailing hemisphere shines nearly as brightly as freshly fallen snow. It rivals one of the brightest objects in the solar system, Jupiter's moon Europa. By the way, Iapetus has a similar feature in its far neighbor, Pan, which has an unusual shape resembling a dumpling. This shape is likely due to the accumulation of material from Saturn's rings on Pan's surface. Mimas, another moon of the gas giant Saturn, is of interest to Star Wars fans, as it bears a resemblance to the Death Star from the famous franchise. Mimas has a diameter of about 400 kilometers and is the smallest spherical object in the solar system. In the past, it narrowly escaped being shattered by a large impact crater called Herschel, which had a diameter about 30% of Mimas itself. The cracks left behind by this colossal impact are clearly visible even on the opposite side of the moon. Next in our selection are Mars' two moons, Phobos and Deimos, named after the sons of the ancient Greek god of war, Ares, who is also known as Mars in Roman mythology. So, their names are quite clear. Interestingly, astronomers had been searching for these moons for quite some time before their discovery. It is said that in Jonathan Swift's Gulliver's Travels, written almost 300 years ago, it was mentioned that astronomers from the flying island of Laputa had discovered two of Mars's moons. What's even more interesting is that Deimos gradually increases its orbit radius with each revolution around the planet, while Phobos, on the contrary, decreases its orbit. So in the future, Deimos might escape into space, while Phobos could crash onto Mars, causing unprecedented cataclysms on the planet. However, this won't happen anytime soon. These are the fascinating and unusual moons that orbit the planets in our solar system. It would be wonderful if more exploration missions were sent from our planet to study this variety of moons further.